computer. I will share my screen of my iPad. Come on. Come on. There it is. All right. So, by the way, so I posted the videos on YouTube, right? And you know, you got to watch them to make sure that they worked. And oh my God, you know, the day you become an adult is the day that you have the question, do I really sound like that? And the day that you become an adult is the day that you realize, yes, you really do sound like that, and there's not a damn thing you can do about it. Okay, so I'm an adult now, finally. Okay, but I digress. So we were talking about quantum mechanical gases, right? So we had derived a couple lectures ago the Fermi-Dirac distributions and the Bose-Einstein distributions for how, or for the expected or average occupation numbers of quantum mechanical energy levels based upon whether or not those energy levels are filled up with fermions or bosons. And then in last lecture, what we did was to apply those rules for how energy levels are occupied to a Bose gas. So we had a gas of bosons. Specifically, they were material bosons, so bosons that have mass and non-zero chemical potential. And we showed how, as you increase the density of particles in the box, that eventually their thermal de Broglie wavelengths will begin to overlap when the concentration or the density hits the quantum concentration. And at that point, or at least around that point, by some factor that was equal, I recall, to the zeta function evaluated at 3/2, the density of particles in the ground state shoots up to infinity. That is, they Bose-Einstein condense. So last lecture we saw why bosons Bose-Einstein condense, and we were also able to calculate what the critical temperature was at which you would expect bosons to Bose-Einstein condense. It was a delight. All right, so now today what we're going to do is talk about one last kind. Well, no, it's not the last kind of gas. It's the last boson gas we're going to talk about, and then probably at the end of the lecture and going into the next lecture, we're going to start talking about a fermion gas, and we'll see how fermion gases behave. Okay, but today we're going to talk about one last boson gas, and it's going to start off not necessarily sounding like what you would expect a boson gas to sound like. All right, so what we've talked about before was we had a box, and the box was empty, right? So it had walls that were made out of some material, but the inside of the box was empty. And into this empty space in the box, we placed a bunch of bosons. There they are. Look at them. Bosons. So cute. Bosons. All right. So now so this is what we looked at previously. How exciting. The gas we are going to look at today is somewhat different in that the box we are going to look at has no empty space. It's just a solid box made out of whatever material it is that you can imagine. All right, so it's a solid box, and in particular, it is a crystalline solid. Okay, and this is what we're going to look at today. All right, so that doesn't really sound like what you would really refer to as a gas, right? So now let's think about how this box is going to behave. So let's zoom in really, really close on a part of this box. Okay, so it is a crystalline solid, and all crystalline means is that the atoms or molecules that make up the material are organized in a regular pattern. Okay, and so just to keep things simple, we're going to say that the pattern that our atoms and molecules are arranged in is just a square grid. Okay, so here are some atoms and molecules that make up our box. And they are arranged in a crystalline grid. Okay, now this material is a solid. That is, it's not like a gas. The atoms and molecules are not free to move around wherever they damn well please. They are held in place in this regular grid. Okay, and the reason they are held in place is a consequence of the bonds between adjacent atoms and molecules. Now, as you may have learned in some of your previous classes, whenever you have two atoms or molecules bound to one another, a really simple model for what that looks like is you can just think of them as connected by springs. All right, so we can think of every one of these atoms and molecules as held in place by a set of springs, which represent the bonds that hold the atoms and molecules together. And I just love drawing these things so much that I'm going to draw all of them, by God. Let me go. I'm getting good at this now. This will please your average YouTube viewer, am I right? Yes. All right, there it is. Okay, and I should state that, for simplicity, we're going to assume that this thing is infinite. Okay, I'm not going to, so we don't have to worry about edge effects. So our grid is infinite, or at least, we're looking at somewhere far, far away from any possible edges so that we don't have to worry about any peculiar edge effects. All right, so there they are. That's our crystalline solid. All right, so now they're held together, but they are not stationary, right? So this thing is going to have some finite temperature. And what the temperature corresponds to is that the atoms and molecules are jiggling around. Okay, so each one of these guys, even though it's held in place, they are going to jiggle around like so as a result of their temperature. And I'm not going to draw these arrows on everything because that would be silly. You get the idea. So they're jiggling around. All right, another way to put it is so they're balls that are connected by springs, and these balls connected to springs are jiggling. What does that remind you of? That is what you have studied since your very first physics class. So each one of these atoms and molecules looks like a harmonic oscillator, right? So you can imagine each of the atoms and molecules that make up a crystalline solid held in place by bonds which function, at least to a first order approximation, as springs, as behaving as though they are a bunch of harmonic oscillators. Okay, now they're atoms and molecules, which suggests that they're not just harmonic oscillators. They are, in fact, quantum harmonic oscillators. Okay, so each atom and molecule in our solid is going to act like a quantum harmonic oscillator. Okay, now, hey, again, we've all taken quantum mechanics class, right? So we know how quantum mechanical harmonic oscillators behave. We know that a quantum harmonic oscillator, the potential is, as usual, quadratic. That's what makes it harmonic oscillator. You stick that potential into the Schrodinger equation, and from the Schrodinger equation, you get the wave functions and the energy levels. And the energy levels for a quantum mechanical harmonic oscillator are these E sub n, which are equal to h bar omega n plus a half, where n can be any integer it damn well pleases. All right, so that's how the atoms and the molecules in this crystalline solid behave. They behave like quantum harmonic oscillators that have these available energy levels. And we got a crap load of them, right? There's a bunch of them because it's a big solid. That suggests, hey, we ought to apply some statistical mechanics to figure out how this crystalline solid is going to behave. Okay, so we know the energy levels, so let's calculate the partition function, because why not? That's statistical mechanics, right? That's what you do in statistical mechanics, is you calculate partition functions. All right, so if we calculate our partition function, the partition function, okay, which I will call, as usual, Z, and I will put on it QHO for quantum harmonic oscillator. Okay, now the number of particles in this thing is fixed, right? So, I mean, you're not going to be arbitrarily adding or removing atoms from your crystalline lattice. And so the simplest way you can think of this thing is as a fixed number of atoms, and hence we're going to do it within the canonical ensemble. Okay, and in the canonical ensemble, the way that you calculate the partition function is you just take the Boltzmann weight, which is e to the minus beta en, and you sum over all possible n. All right, now it's okay, so what are the ENs? Well, hell, we know what they are. We just talked about this. We know they're quantum harmonic oscillators, so the energy levels are going to be quantum harmonic oscillator energy levels. So we plug that in, n equals 0 to infinity of e to the minus, and I'm going to be super explicit here, h bar omega 1/2 plus n over kBt. Okay, so that's what we got to calculate. That doesn't look so bad, right? Okay, so now notice, in this exponent, we have a sum of two terms. The exponent of a sum in your exponential is the same as a product of two exponentials. So you can immediately write this like so. E to the minus h bar omega over 2 kt times e to the minus h bar omega n over kbt. Right? This thing, since so our sum here is over n, right? So the sum is over n. This thing don't have no damn n's in it. So it doesn't care. As far as the sum is concerned, this first term is just a constant. So pull it on out. Okay, so we pull the first term out, e to the minus h bar omega over 2 kBt. And then we have n equals 0 to infinity, e to the minus h bar omega n over kBt. Alrighty. Now, hey, look at that. That looks familiar, doesn't it? So let's rewrite this again in the following way. So again, we got that constant out front. And now I'm going to write this as little z to the n, right? Where little z is e to the minus h bar omega over kt. All right, so in other words, what we got here is a geometric sum, just as we had previously when we talked about bosons, right? So now the question is, what is this equal to? And now we know what it's equal to because we've already done this, right? So this is exactly the same sum that we encountered when we calculated the partition function for bosons filling up a quantum mechanical system. All right, so we know this is a geometric sum, and when we evaluate that geometric sum, what we get is the following. So we get this, again, constant out front, and then our sum is equal to this, 1 minus e to the minus h bar omega over kt, 1. Okay. So this is the partition function for quantum harmonic oscillators. And you will notice that this looks remarkably similar to that which we calculated for bosons, right? So if we just remind ourselves, if we calculate the partition function for bosons, we've already done this. And just to keep things simple, we'll do it with chemical potential equal to 0. Then our partition function for bosons in the grand canonical ensemble with 0 chemical potential, we said that this was equal to n equal to 0 to infinity, e to the minus epsilon alpha minus mu n alpha over kBt. And again, if we set the chemical potential equal to 0, that thing goes away. And what we have is infinity e to the minus epsilon alpha over kBt times n alpha. Okay, so in other words, it's the same damn thing. All right, and this gives you the Bose-Einstein distribution, right? So when you evaluate this thing, what you get is 1 over 1 minus e to the minus h bar omega over kt. So you see this is exactly the same as what we got here for the oscillations of our crystalline lattice, except, right, so this thing here is the same as here. The only difference is when we talked about the oscillations of a quantum mechanical lattice, we get this extra constant out front, e to the minus h bar omega over 2 kt. All right, so in other words, we say that the partition function for quantum harmonic oscillator is equal to e to the minus h bar omega over 2 kBt times the partition function for bosons in the grand canonical ensemble. Okay. So in other words, they obey exactly the same, these oscillations in our crystalline lattice obey exactly the same statistics as a collection of boson particles, except shifted by some constant amount. This is what's referred to as the 0-point energy. Okay, but the 0-point energy isn't going to, it's a constant, right, effectively. And so it's not necessarily going to meaningfully influence the statistics or the behavior of the system. In other words, these oscillations in this crystalline lattice behave statistically just like a collection of bosons. All right, does that make sense? All right, so the oscillations, well, let's do better than that. Let's say the quantum mechanical oscillations in a crystalline lattice behave identically with identically the same as a collection of bosons. A collection of boson particles, let's say. Okay, in other words, the oscillations in this crystalline lattice behave like boson particles. In other words, you can think of the oscillations as particles themselves. Okay, so these oscillations in the crystalline lattice, you can think of as bosonic particles. And these bosonic particles have a name. These are what are referred to as phonons. All right, so a phonon is simply, you can think of it, it obeys the same statistics as a collection of particles. So you can think of it as a particle that represents an excitation in the crystalline lattice of our solid crystal. Does that make sense? All right, cool. Now, so in other words, what you have here is a collection of harmonic oscillators. That collection of harmonic oscillators can start oscillating, and those oscillations in that field of oscillators looks like a particle, right? And so now it turns out that this idea, this is quantum field theory, right? So here what we have is an actual honest-to-God crystalline lattice that's made up of a series of harmonic oscillators. And when you excite that field, it starts to vibrate, and those vibrations look like particles. So those excitations in the field of our crystalline lattice are phonon particles. And so now the idea behind quantum field theory is exactly the same, right? So every kind of particle you can imagine is associated with some kind of field, all right? So for example, the electromagnetic field. All right, when you excite the electromagnetic field, those excitations look like particles, and what those particles represent are photons. All right, so you can think of all of space as being filled up with a essentially crystalline lattice of harmonic oscillators that make up the electromagnetic field, and when you excite vibrations in that electromagnetic field, it looks like a photon. It is a photon. All right, similarly, so what's another one? So electrons, for example. Again, everywhere in space, there is an electron field. And when you excite vibrations in the electron field, it looks like a particle. It looks like an electron. All right. Now, the way that lattice behaves is going to be a little bit different than what we just talked about for phonons and for photons, because the vibrations in that field will yield a fermionic particle. And so the way that the field must behave is going to be a little bit different than our bosonic fields that we've talked about previously, but the idea is still exactly the same. Every kind of particle is associated with some crystalline field, and when you excite that field, it looks like a particle zipping through space. Okay, does that make sense? Or again, a better question, because nobody ever wants to say anything, is does that not make sense? All right, very good. Okay, so that was the last bosonic gas we're going to talk about. The next thing we're going to talk about is a Fermi gas. Let's see how Fermi gases behave. So the next example we're going to work through is an ideal Fermi gas. Okay, so exact same setup. We got a box. Our box has volume V, which is equal to L cubed, because all of the dimensions of our box are the same. We're going to throw in some particles, as we are wont to do. Okay, so it's a quantum mechanical particle in a box. So the potential inside the box is 0, potential outside is infinity. So it's exactly the same thing we've done previously. It's just quantum mechanical particle in a box. The wave function solutions are going to be plane waves. Okay, so the size are going to be plane waves. So it's just going to be some constant e to the I k dot r. And the energy levels are going to be h bar squared k squared over, oh man, I shouldn't have gotten this brave, I believe it's just 2 pi m. And the k's, kx squared plus ky squared plus kz squared, and each of these, I shouldn't say equals. Oh boy, I shouldn't have gotten quite so brave. But another, these things are proportional to some quantum number, right? Okay, so the argument again is exactly the same. When you look at the behavior of this gas in phase space, the coordinates we're interested in are going to be our components of k, or equivalently the components of p, the momentum, and our constant energy levels correspond to a sphere in this k space. And we're interested again in the number of states that live within a shell volume of the sphere in k space. And the answer is going to be exactly the same as what we got previously, right? Because the answer to this didn't depend upon the fact that it was a boson or a fermion. So what we got, whoa, that's skinny. Let me go back to my big fat one. There we go. So our density of points within the grid that correspond to these discrete possible values of our k vector comes out to be just exactly the same thing we had before, L cubed over 8 pi cubed, which you could also write as V over 8 pi cubed. Okay. Now, just as we did before with photons, so when we worked this problem for photons, right? And we said that we calculated this density of points within our grid. And then we said that we had to take this density and multiply by a factor of 2 in order to compensate for the 2 possible polarization states of the vector. Same deal here. So we're going to say that we have, so we're going to say our particles are fermions. Whoops. Particles are fermions with spin s. All right, and depending upon the value of the spin, that will determine the essentially the degeneracy of the states at each grid point. All right, so for example, if the spin is a half, then we would multiply by a factor of 2 because we would have 2 possible spin states. In general, if the spin is s, the factor that we would need to multiply by is 2s plus 1. Okay, so again, so you can try it out for yourself. If s is equal to a half, this gives you 2 spin states. If s is equal to 3 halves, you can plug that in and you'll get, what is it, 4 possible spin states. Okay, so the degeneracy of the number of spin states at each grid point is given by 2s plus 1. All right, so that implies that when we write down this density of grid points in our space, that it is what we had before, L cubed over 8 pi cubed, and then we just multiply by 2s plus 1. There it is. All right. Now, what we want to do is to sum over all possible states, okay, that have the correct energy. All right, and so the way that you would do this would be to, you know, if we had discrete energy levels, you would take this thing and then sum over, you know, the correct radius of your sphere. Again, we're going to make the approximation that the box is so large that our states are approximately continuous. And what that means is that when we sum over all states, what we're going to do is take this, what was previously a discrete sum, and do integral. All right, and so our integral, so we're going to replace this sum whenever we sum over all states with an integral that looks like this: 2s plus 1 rho of k integral over k space. All right, and so this is equal to 2s plus 1 rho of k, as we said before, is v over 2 pi cubed d cubed k. And then we substitute in that this is related to our momentum by p is h bar k. And so this integral that we would do to sum over states would be 2s plus 1 v over h cubed d cubed p. All right, and I don't know if I've used this notation before, but what I mean by d cubed p is just a three-dimensional integral in p space. So this is just my shorthand way of writing this. Okay. All right. Okay, so now again, our energy levels are h bar squared k squared over 2m, where k is equal to 2 pi over L in x, in y, in z. Okay, now, so to keep everything simple, let's first of all look at zero temperature. So let's first look at zero temperature. Okay, so in other words, T equals 0. Now, why do we do this? Well, that's because, again, these things are fermions. So they are going to obey the Fermi-Dirac distribution. And at T equals 0, the Fermi-Dirac distribution is nice and simple, right? The average occupation level, or the average occupation number as a function of energy. Okay, so you have this special value that is the chemical potential. That is also referred to as the Fermi energy, E sub F. And all states up to the Fermi energy are filled. All states above the Fermi energy are empty, where this value up here is 1. So it either has a particle in it or it doesn't. All right, so now, so in other words, what we want to figure out here, these states down here are filled. We want to find out how many states is that. All right, so how many particles do we have? All right. So the number of particles that we have, so at T equals 0, N is equal to the surface area of our sphere, 4/3 pi. And now the radius of the sphere that we're interested in is the Fermi energy, right? So it's the Fermi energy squared. Okay. And now, what we want to look at is, so what I'm going to do is just look at one quadrant of this sphere. All right. So in other words, I'm just going to look at essentially an eighth of this sphere. Okay. So in other words, I multiply this by an eighth, just because those are the positive momentum values or the positive energy values. And let's also assume that these are electrons, so that there are 2 spin states. Okay, so this Fermi energy here corresponds to some particular number of particles, so let's call that NF, like so. All right, and so our energy here, if we take this N sub F and plug it into this energy value, all right, we can then rearrange this thing and get that the Fermi energy is equal to 2 pi squared h bar squared over ml squared in F squared. Okay, so that's our Fermi energy. Okay, so now if we take this and we plug it into here, what we get is that the quantum numbers that correspond to the Fermi energy are 3n over pi to the 1/3. Okay. And hence the Fermi energy is 2 pi squared h bar, I believe that's squared, over ml squared. And then this we substitute in here, we get 3n over pi to the 2/3. Okay, so now the total energy of the gas. Okay, so the total energy of the gas is if we take our Fermi energy as a function of particles, and then we sum over however many particles, or we sum from 0 particles up to n particles, and that'll tell us what the total energy of our gas is. Okay, and again, if we make the continuum approximation, this is an integral from 0 to n of our Fermi energy as a function of n prime dn prime. Okay, and then we take this and plug it into here, and what we will get is 3/5 the Fermi energy times the number of particles. Okay, now, so this is the total energy of our Fermi gas. All right, and now what we're interested in is once you have the total energy, you can start extracting information about the gas. So you can start taking derivatives and so forth in order to determine things like pressure, so on and so forth. All right, so if we, for example, want to find the pressure, so at T equals 0, so from thermodynamics, if we have the total energy, we can find the pressure as the negative derivative of the energy with respect to volume. Okay, and so this is the energy, and the volume is, so again, we've got the that the total energy is a function of the Fermi energy. And the Fermi energy, you can see right here, depends upon the volume of the box. All right, so if you take this expression for the Fermi energy, rewrite it in terms of the volume, and then differentiate with respect to the volume, what you will get is 2/5 N over V times the Fermi energy. Okay, so that is the pressure of a Fermi gas at T equals 0. Now, think about what that means. Okay, so now if you think about the behavior of our classical ideal gas, so for a classical ideal gas, we had derived our old buddy, the ideal gas law. PV equals NKT. Now, what the ideal gas law for a classical gas tells you is that at T equals 0, you just plug in T equals 0 here, and you will see that at 0 temperature, you get 0 pressure. And what that corresponds to is, again, the temperature corresponds to the kinetic energy of your gas molecules. And so as the temperature decreases, that kinetic energy decreases. And at T equals 0, there will be no more kinetic energy. Okay, so in other words, classically, at temperature T equals 0, the atoms and molecules will be completely stationary. If they're completely stationary, then they're not going to be smacking up against the walls of the container that they are held in. All right, and so that's where pressure comes from. The pressure of a gas comes from the atoms and molecules that make up the gas colliding with the walls of the container and imparting momentum to the walls of the container. If the atoms and molecules are not moving, they cannot collide with the walls of the container, and therefore you have zero pressure. But now, from fermions, that is not what you get. So for fermions, even when there is zero temperature, you still get a non-zero pressure. Okay, so for fermions, even at T equals 0, you still get a non-zero pressure. In other words, the atoms and molecules that make up your Fermi gas are still moving. Why? Well, so again, at T equals 0, what's happening is that if we draw the energy level diagram of our system, we're again going to have, a set of discrete energy levels, like so. And the Fermi energy sets, so let's say this is the Fermi energy. So at T equals 0, every energy level below the Fermi energy is filled, and every energy level above the Fermi energy is empty. Okay, so if this is the Fermi energy, then every level below the Fermi energy will have a particle in it. Every level above the Fermi energy will not have a particle in it. And each one of these energy levels has some finite non-zero energy, right? So this particle up here, for example, even though it's at zero temperature, it still has higher than zero energy, simply because the Pauli exclusion principle is preventing it from falling down to a lower energy state. So it cannot do this because of the Pauli exclusion principle. All right, so because the Pauli exclusion principle, even at zero temperature, fermions occupy higher than zero energy levels. So they still move around, and as a consequence, they still exert pressure on the containers that they are held in. All right, so in other words, what we're getting is pressure is a consequence of the Pauli exclusion principle. Okay, and this kind of pressure that arises as a consequence of the Pauli exclusion principle is what's referred to as degeneracy pressure. Degeneracy pressure. Okay, so it's a pressure that arises from the fact that essentially fermions cannot be degenerate. They can't occupy the same energy levels, and the Pauli exclusion principle is preventing them from being degenerate, and this lack of being degenerate leads to a pressure. Okay, so there are lots of places where this is extremely important. All right, so one example where degeneracy pressure becomes important is a neutron star. All right, so a neutron star is the end state of a really massive star's life. All right, so what happens is you have a really massive star, okay, and then eventually that star runs out of fuel. And when it runs out of fuel, all the elements that had you know, been fused together to form that star over its lifetime collapse towards the core of the star. Lots of stuff gets blown off in a supernova. All right. And so what you wind up with is the core of the star is collapses into this ball. All right. And it's you know, it's really massive, right? So this thing is really massive, and gravity is trying to crush this thing. All right. So gravitation is trying to make the core of the star collapse. And at this point, you know, the star's run out of fuel. All right. And so usually what happens in a star is that this gravitational collapse is counteracted by fusion, the pressure arising from fusion. All right. But at the end state of a star's lifetime, when it's run out of fuel, you no longer have fusion holding the star together. All right. So what the thing wants to do is to collapse into a black hole. And essentially, the only thing preventing it from collapsing into a black hole is this, is this degeneracy pressure. So the last stop block against collapsing into a black hole is the degeneracy pressure of all the materials that make up the core of this neutron star. And if you can still exceed this pressure, right? I mean, if the gravitational pressure exceeds this degeneracy pressure, then black hole time. But as long as the degeneracy pressure is higher than the pressure coming from gravitational collapse, then the star will not collapse on itself, simply because it's made out of fermions, and it will stay as a massive neutron star. All right, that was exciting, wasn't it? Okay, so I think that's it for today, and I'm out of time. And so has anybody got any questions about anything before we call it a day? All right, then I think we're done for the day. And my recollection is that on Wednesday, we're going to start talking about something else, right? So we've talked about now boson gases. We've talked about fermion gases. That's it. There's no other kinds of gases. And so on Wednesday, we're going to start talking about a different topic entirely. And that is the, what's it called? Why am I drawing a blank? What the hell is it? Ising model. We're going to talk about the Ising model. All right. So whenever you do statistical mechanics in any kind of actual real world problem, the first two questions you ask yourself about the problem you're looking at is, how do I make this look like a random walk, which we've already talked about? And the second question you ask yourself is, how do I make this look like the Ising model? And so that's what we're going to start with on Wednesday. And we will conclude the class by talking about the Ising model. All right. Until then, folks, I will see you on Wednesday. Oh, somebody asked a question. Don't forget to like and subscribe. Exactly. Mash that like and subscribe button. Adios, folks.